How's it going, everybody? So here we have another video covering section 15.5 on surface area using double integrals. And so what we're going to want to do is we want to find the surface area for some surface of a function f where z is a function of x and y, but above a region D. So for example, we're going to start, let's say this is our region D here, and the surface of your function may be larger, but this is the particular surface that lies exactly above your region D, okay? And we want to find the surface area of just that particular surface S. And so the idea that we're going to be using here, the main point, is, as we do with these double integrals, is you're going to split up your region D into smaller sub-rectangular regions. So for example, here we have a rectangular region Rij that will have delta x in terms of the x direction change and delta y in terms of the y direction. The area of this subrectangle will be delta x times delta y, which gives us our area delta A. And so we're going to want to do that to each particular subrectangle, as we've done in the past. And then the way we're going to do this is we pick a point. In this particular scenario, we're going to pick the top left corner point. Or if you're on the xy plane, this is the positive x-axis, positive y-axis. It's really the bottom left corner point. But regardless on your perspective, we're going to pick a particular point. We're going to plug it into your function. And then that's going to correspond to a point on our surface S, okay, with a particular z value. And so you can't really tell from here, but then above this small subrectangle, there is a piece of our surface S right here that lies above that subrectangle here. And to help us find the total surface area, we're going to find the surface area just above our small little subrectangles. And remember, these are going to be really, really small subrectangles. So these little small surface areas, delta Sij, corresponding to the point xi, yj, we're going to find the surface area of these little small ones, and then add those up to approximate the total surface area that we want. But now, how exactly do we find this small surface area here, delta Sij? Well, what we're going to do is we're going to consider at this point, we're going to consider a tangent plane, okay? Now, this is a small picture here, but let me see if I can do nice and long. Imagine you had a big tangent plane at that point, okay? Because we've learned how to find tangent planes, but we only want to consider the tangent plane region above Rij as well. And if we do that, this small piece of our tangent plane is going to be a small parallelogram. And we have tricks on finding the area of parallelograms. Okay? So that's the main strategy that we're going to be implementing here. So let's recap real fast. We're going to start with a rectangular region D and generalize it, and we're going to be able to generalize this rectangular region D to any kind of region, as we've done in the past. Things to note is that at the point xi, yj, the small surface Sij is above the rectangle Rij. That's the blue little piece I drew here. The small tangent parallelogram Tij on the tangent plane to the surface area, to the surface above Rij. So what I'm saying here is that above this point, we have the small parallelogram that's tangent to the surface corresponding to this point. And this small parallelogram has a certain area which we're going to call delta Tij. And what we're going to be using is the fact that this area of the small piece, this small little piece, that surface area is going to be approximately the area of this small parallelogram. because as these small subrectangles get smaller and smaller and smaller and smaller, and this all gets more fined with smaller little subrectangles, these small little blue chunks of our surface, they're going to have a surface area that's approximately going to be close to the value of the surface area of our tangent parallelograms. And that's the trick that we're going to be using. Okay, that's the strategy. So to help us find the surface area of S, we're going to find the small surface areas of Sij, but to find the small surface areas of Sij, we're going to find the areas of our small little tangent parallelograms, Tij. So now what it comes down to is, well, exactly how do we find these small little areas? And this is what we're going to do. So at this point, remember that S is the surface of a function. Okay, it's the surface of the function f. And at this point, the directional derivative corresponds to the tangent line where x varies and y stays constant. And the partial derivative with respect to y gives us it has a relationship to the direction of the tangent line ty, okay, at this particular point. And what was that relationship? Well, it was that the direction vector of tx is just analyzing how the x, y, and z values are changing at this point. And so when you take the partial derivatives and try to analyze how they're changing with respect to x, remember that you're holding y constant, but z and x are going to be changing, and x changes with respect to itself, y stays constant as x is changing, so there's no rate of change, and z is changing according to the partial derivative of the function at that point. That's exactly what this value is supposed to give us. And so this direction vector of tx is going to be given by this direction, which I'm calling vx. And similarly for the tangent line ty, its direction vector analyzes how the coordinates are changing at that particular point pij, but with respect to y. And so you're holding x constant, so there's no rate of change. Y changes according to itself, and z changes according to what the partial derivative of the function with respect to y is giving you at this particular point. And so this is its direction vector of the tangent line ty. And so if I look at those vectors, vx and vy, they're going to be parallel to the vectors a and b that give you the that construct this parallelogram, as we've talked before when we were doing vectors. Okay, but the thing is that these direction vectors don't have the necessary components that we want, because we want this length here of this vector to have the change in the x-coordinate to be delta x. And we want the vector b to have the change in the y direction to be delta y. And notice that vx does not have the change in the x direction to be delta x, and vy does not have delta y as its y component to give us the change in y. And since we want these vectors to correspond to the lengths according to these tangent parallelograms, well, what we do is we know we want A to be parallel to the vector Vx because we want it to be in the same direction as the tangent line Tx. But because we want the x component to be delta x, we multiply V of x by delta x. And so that gives us our desired magnitude for the change in x. And similarly, we want B to be parallel to the vector Vy, but Vy has y component 1, so we multiply it by delta y to give us the desired y component. Okay? So then these vectors A and B for any given point will always be of this form here, where the z component of those vectors will be determined by the partial derivatives at these points xi, yj. Okay? Okay. And how do we find the area of those small parallelograms? Well, remember that since vectors A and B are what the lengths that help us construct this parallelogram, we've learned this when we were doing cross products, that area equals the magnitude of the cross product of these two vectors that we've just constructed. And so then we take the cross product of these two vectors with the components that we just defined. And when you take the cross product of these vectors, you're going to get this vector, where, remember, the first component, for example, you're going to be ignoring the first column and the first row, so then you get 0 minus the product of these two, which is exactly what this is giving you, and so on for the other ones. Okay? And so then what we do, since delta x and delta y, by definition, was that area, let me remind you again, where was it, up here? Delta x times delta y is exactly the area of these that we defined to be delta A. I can rewrite delta x and delta y times delta y as delta A. And since all of these have delta A here, this is delta A, this is delta A. Ooh, I like this color. It's pretty. Sorry. Delta A, we can factor it out as a scalar multiple. And so we get delta A outside, and then this turns out to be the cross product of this vector. But because we want to take the magnitude, then we go ahead and we take the magnitude of this times delta A. And so that's the components each squared. And so then we get that the area of that parallelogram Tij is given by this expression here, using the partial derivatives of your function evaluated at those points. And so from this is giving us the area that we wanted. So that was these areas, and then that was approximately equal to Sij right here. And so we're gonna, the smaller and smaller that our region D gets split up, the closer and closer these two areas start getting to one another. Then you let the number of sub rectangles go to, you partition the x-axis here, this interval, into an infinite amount of subintervals, and same thing with this one, which will give you an infinite amount of sub little rectangles. And so you take the limit, as we've done in the past with these double integrals, using this expression to give us that desired area. And so then we get that the area of the surface of an equation where z is a function of x and y lies within that particular region D, if we have that f partial of x and f partial of y are continuous functions, the way we find the surface area of the surface of this function above the region D will be by integrating this expression. Okay? And another way of viewing this expression is just saying the partial of z with respect to x squared plus the partial of y, the partial of z with respect to y squared plus 1. Okay? And so this is a formula. Let me just remind you again, just because students forget what you're doing here. This is giving you the surface area of the surface of f above a region D. Okay? Above a region D. And so you don't integrate the function. Okay? You're not integrating the function. You have to take the double integral of the function of the square root and then take the partial derivatives of this function with respect to x and with respect to y, square them, plus 1, and then this is a function that you need to double integrate in order to get that surface area. All right? All right, so this is the constriction of it. Let's take a look at another video where we're going to see an example of how to figure that out. All right, folks. Take care. Bye-bye.